Hello, welcome to this Cosmos DB session. Jack of all trades, master of many. Um, you're gonna see what I mean with that during the next 1 hour. Cosmos DB is really a different type of beast compared to whatever you have seen so far. Not only limited to cloud hosted database services, but whatever you can imagine is a in the scope of a database. So this is gonna be a fun. I'm hoping it's gonna be a fun um, session. So let's start. Let's dig into this slowly, and in order to do that, we are gonna start with a little bit of the Cosmos DB's history. So it's like, where did this come in really from? I mean, what is this thing? I mean, did Microsoft, come up with this thing, in a, just in a build announcement or something? What's the history? So this goes back to 2010, actually. Now that we're kind of getting to the end of 2020, it's been 10 years. The name wasn't obviously Cosmos DB back in those days. It was Project Florence. And if you remember those days, I guess it was 2008 when I first did my, Azure presentation in a university. And, we were slowly getting started with cloud app development. Public cloud services were getting, hot, and we were starting getting into this space. And I'm not sure what the exact date was. I can actually check on that, but I do remember since 2009 or something. I have been in various meetings or people were asking Microsoft, hey, what are you gonna do, guys, with the NoSQL thing? I mean, there is no NoSQL product from Microsoft, and especially if you look from the .NET developer's perspective, you expect, something that is native to the platform, and by platform I mean the Microsoft stack, something that has better integration compared to whatever else out there, where .NET might not be on top of their list, right? So that was a discussion that was going on, and it looks like Microsoft internally needed this so that they started working on Project Florence in 2010. So then I was one of the lucky ones. Our company was one of the lucky companies because we were looking into a NoSQL database hosted in the cloud. I'm not gonna call out names, but we ended up picking one, and then we ended up hosting that on top of virtual machines in Azure. Our solution, it was a SaaS product that we were building back in those days, and our solution was totally hosted on platform as a service offerings, but we had to manage our own infrastructure to run a NoSQL solution. Back in those days, again, it looks like, yeah, let me take a look at the date of this article where I was the interviewee. It's 2014, and 2014 there wasn't even a single NoSQL service provider on the Azure Marketplace or anything like that. So there was no PaaS or SaaS or whatever you call it, managed NoSQL service on top of Azure back in those days. So you had to do your own thing. And to be honest, even the other NoSQL, software providers out there, they didn't even have the appropriate licensing that would allow us to scale and accommodate spikes. They were selling, for example, they were selling CPU core licenses that doesn't really make sense if you're gonna use that CPU core just for 5 minutes because you just want to scale to that to that VM for just 5 minutes. It doesn't make sense to purchase a full CPU license. So those were the good old days. I'm not sure if those were the good or bad old days, whatever. So and that's when I got, thanks to the team I was working with, our team got into DocumentDB. So we got into DocumentDB when it was private preview, and we were lucky to be one of the, again, I guess it was just 3 companies in the global launch. One of those 3 companies in the global launch being part of the DocumentDB's global launch. So we got our hands on DocumentDB pretty early in the game. But keep in mind, and it's been already, 5 years in, that Microsoft was building this product and using it internally, right? So it takes a while to productize something if you want to ship it outside your organization. I mean, and if you're going to use it internally, that's a whole different story. Then another surprise, this was really a surprise, by the way, came in 2017, and overnight it was doing a build day 2 announcement, if I'm not mistaken. It was an overnight conversion of all DocumentDB. I mean, no one had to do any code changes or anything like that, but overnight, when you logged into the Azure portal, you end up seeing a new name for the service that you have been using for years. And by years, I mean 2 years. But anyway, so all the DocumentDB databases, DocumentDB services, they changed names, and we started calling them Cosmos DB. And there was a reason behind that, because till Cosmos DB came in, till the name change came in, DocumentDB was just a document type database. But with Cosmos DB, we're going to go through this during this session. But with Cosmos DB, we got multimodal support and multi-API support, which kind of makes this, this database I mean, it's totally up to you how you want to name it. Essentially, if you want to, name it with a particular NoSQL database type, then it depends. It depends to what what API you pick, what data model you pick for yourself, and then you can name it whatever you want. But as a product, Cosmos DB, just because of the fact that it supports multiple data models and APIs, the name of the product couldn't be aligned with a particular, NoSQL type anymore. And it made sense. It wasn't just, a marketing name change. It was from that point on, because of the features that the product had, it was pretty much a must. You couldn't call it a DocumentDB anymore, because it would just be not fair to the product, essentially. So that's the history. And while talking about multi-layer and multi-API, let's look at what the high-level picture is here. So we got the major features. If we start from the bottom to the top, the major features are, first, I mean, this has to be a cloud database product, right? Cloud database service. So it has to be turnkey, and it has to provide turnkey global distribution. It has to be global, right? So that's important. It has to have the ability to scale, storage and throughput, right? It has to have that ability. It has to have, that SLA that wouldn't really hurt our composite SLA when we are building a SaaS product. I mean, every piece of, service you're adding into your architecture, obviously it might, it will take down your composite SLA, but at least the contribution should be at minimum. And, there's low latency guarantee SLA. There are 4 different SLA types that we get out of Cosmos DB. But this is just one of them, and we'll go through those one by one. And the other one is, the distributed nature of this database service then, brings some additional questions like, hey, what I'm going to do with the consistency levels, what do I have as the options, because I want to trade off consistency to my other metrics maybe, and how much flexibility do I have there. So that's another beautiful thing that we get with Cosmos DB. We got 5 different consistency levels, and we will go through those as well. And we did discuss the comprehensive SLA stuff. We will go into the details of this as well, but high level, those are the major features we get with Cosmos DB. Then on top of that, we got those 4 different data models. We got key value. I mean, these are all different NoSQL data models, right? NoSQL, I mean, you can go out and, find a NoSQL product that only does one of these 4. So there's key value, option, column family NoSQL option, document type NoSQL option, which was coming back from the document DB part, and then graph. We got graph as well. So when you create a Cosmos DB service account, you pick one of these, right? And you pick what you really want as your data model. And then you got APIs. And by API, I mean, how are we going to expose this data to your application, right? And obviously, it looks like in this diagram, it doesn't look like there's a one-to-one mapping, and it doesn't have to, but in some sense, it does. So you go with Gremlin if you're going to use Graph. You go with SQL if you're going to use Document, and so on and so forth. So the most popular ones, I would say, the SQL API, where you can send T-SQL commands to your NoSQL database, which makes it really easy for you and your team to onboard to this to this new product without really learning a new language, right? And then there is the MongoDB API set, which helps applications to migrate to Azure and use Cosmos DB for all of the MongoDB developers. Essentially, they can come in and start using Cosmos DB APIs for MongoDB. So these are the two popular. Then comes Gremlin, and the popularity in this context is just my perception. I have no data to support this, but as far as I can tell on the community, that's how the popularity goes. So Gremlin, Graph, Cassandra, and Table API. I guess Table API should be on top of the list somewhere between SQL and Mongo, because Table API is actually an API that we use for years since Azure came out, right? Azure Table Storage was part of the Azure Storage system, and it is still, but the Table API that was premium at one point, it was called Premium, it did migrate back over to Cosmos DB. So we got the Table API to be able to talk to Cosmos DB and enjoy all of that, the consistency, the premium support, the high level SLAs and all that stuff, and scalability, replication, and all that, compared to and multiple indexes, a lot of flexibility that we can have, and still use the Table API against Cosmos DB. The other table service that we already knew and which was part of the Azure Storage services, it's still there. It's still as it is. It's still useful as it was in the past. No problems with that. But keep in mind that if you're looking a little bit more, but still use the same API set, you can definitely use that with and Cosmos DB. So that's pretty much the whole picture. Now we will start going a little bit into more details on how is this thing moving on, right? So one thing that is important to understand is, with Cosmos DB, when it first started, it had, I guess I have another slide about this, but when it first started, the first time Cosmos DB came out, there was a one master and multiple slaves type of, one write and multiple read I got to start from scratch, not partitions, but regions. So you could have, multiple regions, as many as you want. And by the way, the Cosmos DB service itself is a Ring 0 service, which means it's deployed on every Azure data center that you can imagine. So you can have read scalability, but write scalability was a little bit of an issue, especially if you consider cross-regional deployment. It's not the case anymore. So if you go out and do some research, you might see some, stale information about this. But right now, write scalability is around the world. You can have read and write, regions all over the world, and you can scale from both perspectives, having the low latency, the SLAs and all that, and the consistency model and the conflict management that we will go through. All these benefits, they do apply to multi-master, read-write in any region. In order to enjoy multi-master, though, you gotta enable that, because it's not, I'm not sure if it's enabled by default, by the way. I'm not 100% on it, but you can enable multi-master if you want to have multiple masters, which means if you want to have multiple write regions. If you don't enable that, you will have a single write region but multiple read regions if you start doing geo redundancy. So you can still do geo redundancy even if you don't have multi-master, right? But you will simply be distributing your reads instead of the writes. Oops. Okay. So how does that happen? Simply you go into the Azure portal and you pick the regions and you click save. That's pretty much it. That's it. There isn't a lot to talk about this on this slide, to be honest. It's crazy easy. You don't have to do anything. I mean, there's a single line of code that you might want to change in your apps if you want to. First off, you need to make sure that this, let me see, I should have a highlight in here. Yes, use multiple write locations is true. If you're using multi-masters, make sure that's enabled in the SDK as well as part of the connection policy. And then, you tell your application, the locations, the preferred locations in a list in the SDK so that the application knows which one to go first and be able to fall back to the other one. And that's pretty much it. Yeah. Okay, so what's the difference? I mean, we did talk about this a little bit, but if you look at, let's start from multi-master, right? In multi-master, read and writes are routed across your preferred regions. If you have multiple deployments of your application in multiple data centers, you will have different configurations about your preferences. Obviously, the first thing that you're going to want to connect is the local deployment of your Cosmos DB, local replica of your Cosmos DB database. So, and the SDK will try to go through those preferences that you define in your configuration. And the SDK, if you go with single master, then writes will go to the primary that you selected, and you can enable automatic failover if you want. If you enable that, it can still fail over to another read location if you want to. Otherwise, writes will go primarily with the first region that you selected unless a failover happens. There is a manual failover option on the portal if you want to test it out. Reads are pretty much the same with the multi-master. Reads will be sent to the preferred region, and even if writes do not exist in that particular region. So yeah. So what about consistency levels? Obviously, in a distributed environment, consistency is a big problem. The data is being replicated across regions, and what is this version that we're gonna get from every region and so on? Do I have the latest version? Do I have an old version? And is that okay to read an older version? Maybe that might be based on your scenario. Long story short, the answer depends on the consistency level. The answer to all these questions depends on the consistency level. And if you look at Cosmos DB, we got 5 different consistency levels, which is amazing. Some of those are pretty familiar, right? I mean, the strong consistency, I guess, is familiar to everyone. Eventual consistency, again, is familiar. Session consistency, again, is familiar. But moderate staleness and consistent prefix, they might sound new to you, and they give us additional options to decide what type of trade-offs we want to lay out in the mean of latency, availability, and throughput. So yeah, and all these, you can have a consistency, default consistency per account, but you can override that consistency level per query, per request basis as well, which is pretty cool, to be honest. So what is this about? Let's start with bounded staleness. So you essentially set a bound on the Azure portal and decide how far you can lag behind. It can be an interval, it can be a time. It's totally up to you, and you decide how far you want to be left behind. A particular replica should be left behind. Keep in mind that this is between strong consistency and session consistency, right? This is better than, a little bit more consistent than session, but it is not strong as strong consistency. So you decide a time or a prefix, how many times you want to be, how many versions you want to be behind. Then we got session consistency. Session consistency, I don't think we're gonna go through this in detail, but essentially it's reading your own writes and making sure within a particular session you got consistent results. I'm just taking a look at my slide deck to make sure I'm not missing any details here. Yeah, that's it. Oops, did I go back? I guess I did. Oh, what's happening? Give me a second. Okay, bonded. Oops. Bonded staleness. Bonded staleness. Why do I have this twice? Oh, that's interesting. Okay. So, in order to relax the consistency, if you want to, what you can do is, like I mentioned, you can override consistency per request basis, and this is just a simple, example in a C# code through the SDK. You can specify consistency level with every request that you are sending to the service. Okay, what about conflict management? There are going to be conflicts, right? So we got a couple of different conflict management strategies that we can use. The first one is last writer wins. That's the default mode. The second one is defining a user-defined procedure to decide who is gonna win or not. And then there's a custom asynchronous model that is only available to SQL APIs today. So how does that work? So last writer wins. It's pretty easy. You need to define a property that is going to be used to solve the conflict, right? In this case, if you look at the right side of your slide, you can see that conflict. I'm not sure if I highlighted that. Let me see. Yeah, I did. So user-defined ID, you got an incremental ID or something. So user-defined ID 3 or 4, and then the backend decides which one is the latest, and you have to set this up in the settings for every table that you have in the conflict resolver property. In this case, it's user-defined ID. So it's available for all data models, and that is it. So, and the backend will decide which one is the latest based on that. So you can use a custom user-defined procedure as well. In order to do that, you got to go into, again, settings, but this time there's a conflict resolution stored procedure field where you can write your stored procedure's name. That's how you register your stored procedures. These stored procedures, they have to have a special signature. We'll look into that. And the conflict will be dropped after the processing is done. If the stored procedure fails, then obviously you get an error back, and yeah, they go back into the conflict feed if you want to process the conflict feed and process that conflict asynchronously. And there we go. This is the custom user-defined procedure. In this case, the name is whatever. I don't think we care about the name at this point, but you can look at the parameters and all that. Oops, let me go back. Can I go back? Okay, great. So you can see the name and the parameters, and in this code, we actually decide if we want to, yeah, essentially we do the conflict management. Okay. The asynchronous approach, you leave the stored procedure field blank, right? You select custom, and you leave, you say custom, like merge procedure custom in here. I'm trying to, let me show you. It looks like I didn't have highlighted there. Anyway, you can see it in the screenshot here. I'm trying to show with my pointer right now. Merge procedure. And you leave the stored procedure field empty, which will make sure all of the conflicts are sent into the conflict field, conflict feed. Sorry about it. And then you read the conflict feed and resolve all of the conflicts asynchronously. Yeah, that's what it is. Perfect. Yeah, in this case, it's totally up to you how to decide asynchronously to solve your conflicts. So latency. So the latency question is, this is a little bit fun with Cosmos DB because, yeah, we will. So the thing is, The latency does not, I'm going to say this once and then explain. The latency does not depend on the complexity of your query. It might affect, but it does not. Think about it this way. If you have a complex query, there might be a chance that your latency gets higher, but there's a higher chance that your latency will stay the same, but the cost of that query for you will be larger. And what I mean with cost, we will look into that. But for now, what you should keep in mind is that, the Cosmos DB service tries to hit its latency goals, even if you throw a lot of, a lot of work, right, essentially. Because the goal is to, there is a guaranteed millisecond latency worldwide. There are exceptions, obviously, if you have a user-defined functions which does some crazy stuff that no one can guarantee you, under 2 milliseconds read. But unless you go into these, areas that are exception, then you will always have a guaranteed worldwide latency, both for reads and writes. The primary goal is for reads around 1 KB size. There's a 2 millisecond latency guarantee for 15 percentile, and under 10 millisecond under 10 millisecond latency guarantee for 99 percentile, and so on and so forth. So as you can see on the table on the slide right now, those are the milliseconds guaranteed. And as you can see right now, the only metrics that are worth mentioning is the size of the data, not essentially the complexity of the query. But again, if you start using things like store procedure and UDFs, then those are exceptional cases and they will be out of this guarantee anyways. Yeah, I mean, that's one important thing, obviously. How does this service accomplish this performance? Everything is automatically indexed. You can customize indexes, but everything is automatically indexed. That's important to know. And all of the storages that you have in Cosmos DB, all of them, there is no exception. You cannot set it up to be different, or you don't have to set it up as an, solid state drive, but all of the, storages are SSDs, and everything is automatically indexed by default. That's how you can come to this beautiful performance guarantee. Yeah, synchronous and automatic indexing and sustained ingestion rates, no schema or index management needed. That is correct. But if you do that, because your index sizes as part of your storage cost as well, so you might want to do some index management in order to save costs, but you don't have to. Obviously, there isn't any schema because it's NoSQL. But again, if you want to, customize your indexes and make sure, I mean, let's say that you're not, sending any queries for a particular field. Why would you index that, right? In that case, you might not want to index it and spend, time and money to even keep the indexed output, the index storage. And pay for it. No schema versioning needed, no schema migration needed. I know it's an interesting wording saying no schema migration needed, because schema migration, based on the nature of NoSQL, there's no such thing, right? Okay, so we did talk about this. We got availability SLA with 5 nines for all read and writes, implicit fault tolerance, no need to failover, and yes, I'm just trying to make sure I'm not, skipping anything here. So provision throughput, we did talk about this a little bit. Like, I mentioned that, hey, you can throw some complex queries and you will still get the latency, but you will, the query will cost you more. So this is where I'm going to explain a little bit more what that means. So there is this thing called, this unit called, RU. RU is the cost of a particular query that you are going to pay for. It's a new unit it's not equal to anything that you knew so far. It's a combination of a couple of things. It's called a request unit, but doesn't mean a single request is one RU. It might be or might not. It can be more than that. Obviously, not all requests are equal, and that's why every request has a different RU result. You might have a really complex query. The result of your query might return a single row or hundreds of rows, a small data set or a large data set. Your request can call UDS maybe and require more compute power, so on and so forth. So every query has different requirements, and the underlying system makes sure all of these requirements are met. And when it does that to hit all of the SLAs, then obviously for some queries you have to throw more processing power. For some queries maybe you have to throw more IO, and someone has to pay for it. So with that, every query that you write has to cost different, right? They can't be equal, and that's where RU comes in. It's essentially, let me read this one, a normalized quantity of request units based on the amount of computation, CPU, memory, and IOPS required to serve the request. Yep, that's pretty much it. So here's a table. I mean, you don't have to, I always forget these calculations, to be honest, because there's an easy way to see these when you're writing code. Every time you send a query, you actually get a response back that includes how much RU a particular query cost. And that really helps you optimize your code as well when you are developing. But just to give you a sense of how things are being calculated. So let's say you got an item, you're reading an item that is 1 KB size, and you did 500 reads per second and 100 writes per second, which means you got 500 plus what is that? Yeah, 100 writes per second. Okay, so it looks like every read is 1 RU, but because we have 500 per second, we're going to pay 500 for reads, 500 RUs. And then we have 100 writes. Writes cost 5 RU for 1 KB, which means we're going to pay another 500 for 100 writes a second for a 1 KB data item size. And the total will be 1000 RUs. And yes, this feels like there's still, there is still no mention of compute, right? There's the item size, the number of reads and writes, but there is still no mention of compute, which is definitely incorporated. So I would say it's not as easy as it looks right now on this one, but those are just simple guidelines to help you out to understand how things are being calculated. Here's an example. I don't remember how many. I mean, this is an example that I did myself, so I don't remember how many rows were in that table, but I sent a single select star from C, which is a select star query against the collection, and it looks like there was more data than 1 KB in there. A single select star from C based on the amount of data that it returned did cost 2.87 RU. So my point is, even this might look crazy simple for a query, but again, even if you're not using compute, you're using IO, you're using bandwidth and all that stuff, so this is gonna cost a little bit. So another query is this one: select star from C, where contains c.name sample. So I'm doing a lookup on the name of all these items in the collection, and the cost is 2.45. So isn't that interesting? Because it feels like when you look at the query, it feels like the second query is more complex, but it costs less. My guess is, in this case, because the amount of data we are returning back from the query is less compared to the first query, we have to pay less, even though from a compute perspective, this requires to go into the index, and this might cost a little bit more from a compute perspective. I'm not, I'm not sure. I can't be sure. I have no data to support my argument. But, if you, I mean, if I give you these two queries, I'm sure you're going to say, yeah, this looks a little bit more complex than the first. But it's not. But again, it depends to the size of the, if there are, 1 billion rows, which was definitely not the case in my demo run. But, you know what I'm saying. So, and on the right hand side, you can see a simple screenshot from the Azure portal where you can run a query in Query Explorer, and on the underneath, I'm not sure if I have, no, I don't, yeah. You can see the request charge here, down here. And when you run your queries in Query Explorer on the Azure portal, you can straightforward see how much it costs you. In this case, this was 2.27 RU. It looks like the query in the screenshot is a little different than the query on the slide. It's querying based on the ID, which looks like it's much more cheaper compared to a string contains query, which makes sense. Yeah, it makes sense, right? So, what about a small demo? Okay, so I have this thing up here, this small project. Let me see. Okay, I'm gonna remove myself so that we can see this a little bit clearly, and let me. Okay, here we go. So this is what we have right now. This is a small, application that I have here that simply does a lot of inserts into the Cosmos DB account that we have here. I will be using the local Cosmos DB emulator. I have it installed and it's open up right now. Let me spin it up. Here we go. This is my local instance. You can download this and install and run this locally. There's an emulator that you can run locally here. And in here, I got a database called DB. Right now, there's nothing in it. It's all empty. I have nothing in there. So, okay. When I run this application, if we'll look into the configuration, you're going to see that, I got the endpoint URL hitting localhost. I got the key, database name, and all that. And we will, target, we will create a collection that will be provisioned for 500 RUs by default. And then we will try hitting that. We will, send 200,000 documents into there. And when we look into this code does the creation and all that. And let me see where the actual line of code is. Partition collection creation. It should be a little bit up there. Insert document. Okay, where are we? Request charge. There we go. So this is the request charge. Every time, in this case, we're creating a document, and as a part of the response, we are actually getting a request charge. And this will help us, there are a couple of things that we can do with this. First off, we don't have the time to do the demo about all this, but when you create, and let me show you for a second here, when you create a new container under a database, you can actually, decide how much throughput you want to have as part of this container, which is provisioning. I do have a couple of slides about this, but we'll talk through this. But, you can decide auto scale as well, which will make sure, it deprovisions resources that you didn't use so that you don't pay. But if you pick manual, this is, static provisioned RU for your particular collection. And there's another API that Cosmos DB provides that you can change this number dynamically. So you can do something like, when your application is working against Cosmos DB, we will look into this. I do have a couple of slides about this, but you can actually, your application can understand, hey, I'm sending a lot of requests to Cosmos DB. Maybe I should send another request saying Cosmos DB to scale itself a little bit more because I'm going to need more RUs for the next 1 hour. So your application can decide if it wants to, Or, you can define, if you go into auto scaling, you can define an upper limit and at least make sure, you can swim under that limit without worrying about, scaling decisions. And auto scaling, by the way, is something new that came in recently for Cosmos DB. So request chart is really helpful to understand which of your requests is really costing a lot. So I'm gonna put a debug point here, and I will run this application so it will start hitting the local environment with a lot of insert requests. There we go. And oh, there we go. First request 13.9. So in this case, we're sending the same request, same document, so it's going to be always the same. But what you can see is that out of a simple create document, we can always get our request charge and understand how much this costs us, even in the SDK, and maybe dynamically do something like I've mentioned previously. So I will go in here, oops, and right now it looks like our application is scaling slowly, warming up. So we should be able to go up to 500 because that's what the application provisioned initially. So let's give it a little bit more time. Meanwhile, I'm gonna go back to the portal if I can. There we go. Let's look into there. Okay, this is the collection that we have. When we go into scale settings, you can see that it's fixed to 500. Cool. Okay, it looks like it's still scaling up. Okay. Give it a minute. $401. It took a while. And meanwhile, if you go back and look at the items collection, you're gonna see that there's a bunch of those, and this is just dummy stuff that we're inserting. And it's always the same document. So did we hit 500? Not yet. I don't want to leave this and go back to the slide, but because then I forget and it runs in the background all the time and it finishes to insert the 200,000 documents. The point is that it's really scaling very slowly though. Okay, let's leave it as it is. I'm gonna make sure I don't forget that. And we're gonna come back in a minute. Okay. So this was the code that we could use. Essentially, this is a different code that I wrote back in the day. So this is doing again a create document, and then getting the request charge and adding it to on top of a query host and so on and so forth. So request unit management. So this is about the provisioning that we did talk about. You can provision a single partition container if you think that's going to be enough. You don't have to specify a partition key in that case. But if you want to go really scale up, then you're going to need a partition key essentially, and you're going to need a partitioned container where you can have unlimited maximum throughput. And if you look at the code on the screen right now, that's actually an example of a C# code that actually sends an offer request to scale the current container to a different provisioning through C# code. Great. So what effects are used? We did talk about this a little bit. The item size, the property count, indexing. Yeah, effects are used. Everything is automatically indexed. You might want to disable some of those if you want to decrease your RU costs. Data consistency affects that as well. I mean, strong consistency costs more than session consistency, for example. Index properties, lazy indexing can help, but index properties like mentioned previously, will affect the cost. Document indexing, yep, that will affect as well. And query patterns, if you have UDFs, predicates, and all that stuff, will affect your RU cost as well. And script usage, if you got triggers and that type of stuff, that's going to be included in your RU cost. So this is pretty much a full list of things that affect RUs. And if you go into the Azure portal, you can actually see all of the graphs that shows you, you know, how much RUs you're using for, you know, update requests and all that. You can see the request charge here, number of requests per hours, and on the top, you know, left, you can see your SLA line and your actual availability, which in this case is 100%, is higher than the SLA. So what if you exceed your RU? What happens? There you go. You get an HTTP for 429. It gives an additional header telling you, you know, how much time you need to get back on track with your RU, usage, RU left, or whatever we want to call it. So in this case, you know, you either wait for it or, you know, maybe send a request to make sure you scale up so that you don't get this HTTP 429 again the next time. And when we talk about, you know, the partitioning, you know, the partition key is important, and this partition key strategy is very important as well to be able to really get most of the most performance out of this platform, right? You need to make sure you select a partition key that helps you target a single partition with all your queries, because cross-partition queries, they're not under SLA. The SLAs apply only to a single partition query, because if you're going to need to do cross-partition query, then, you know, it's going to be a lot of round trips and so, and there's no guarantee how fast you're going to be. I mean, you can still get under 2 millisecond read, for example, per partition, but based on, you know, the number of partitions that you're going to hit, and if you can properly parallelize that, or, you know, if you go sequentially, it's going to take much longer, so on and so forth. So it's critical, and it's important for all data models. Yeah, if you'll look at from a high level, what we have here is we got fault domains, cluster, machines, replicas, and Cosmos DB database engine. I just wanted to give you this big picture to you because, you know, it's kind of important to understand that, you know, you got multiple copies and replicas even in a single machine, and then you got the clusters and then regions distributed across the planet. So when you have your tables, collection, or graphs, which are kind of the same thing from Cosmos DB's perspective. These are just different APIs and how things are named, but essentially these are containers, right? In the case of if you go with Graph API, every container, you know, is represented as, you know, graphs, and then collections or tables, depending on what API you use. And then we got resource partitions in every region. Regions are replicated and globally distributed, and in every region, what you got a replica set, and every replica set has a leader and a follower. So you got multiple replicas within the replica set as well, within the region as well. And writes go to the leader, and reads get distributed across all of the copies. And this is within the region, by the way. This is not about multi-master. In multi-master, we were talking about, you know, regional distribution of writes. In this case, we're talking about, you know, the architecture within a single region. So having a leader and followers, that this concept does not change based on if you have multi-master or not. This is within a single region. Okay. Yep. I'm gonna skip this one because I don't think this adds more information. So writes and reads are distributed. This is a little bit important to understand that there are 3 replica sets between a single region as well from a consistency perspective. And when you're reading data with partitions, this is an example of query that you can send. Essentially, you know, include a partition key and send your query that way. This is the SQL API, and the SDK will understand to hit a single partition, and it will only send the query to a single partition. if you do this, if you simply, do not mention a partition key or anything like that, then this is going to be a cross partition query, but you still need to explicitly mention, in the SDK enable cross partition query equals true, because otherwise it's not going to work. So again, this gives us the message that cross partition query is definitely a deal breaker. It's not a best practice. If this is something you end up doing a lot, you find yourself doing a lot, you need to go back and think about your partitioning strategy. Unless your data set is very small and you picked a non-partitioning container. Let's go back for a moment, because it looks like, yeah, we got 538 RUs and it's pretty much static. It's not going higher than that. Let's try to increase this to 600 for a moment and save it. So our capacity did increase, and instantly you can see that our RUs are increasing as well. And this is just local testing, right? This isn't like a perfect simulation of how things will work, but this shows our application is able to put more load now that there is more available. Perfect. I'm going to close this one up and go back to the slide deck. Great. So reading data with partition keys, you can have, look at the SQL command here. It has the mention of multiple partition key values. This works. The SDK is able to understand. This is still a cross partition query, but this doesn't go to all of the partitions, right? This goes only to 3 partitions, which is nice. Because this isn't going to require to go to all partitions and do a scan on all over the place. This will still perform better than the previous one. And it's important to mention this max degree of parallelism as well. Make sure you pick an appropriate one, because otherwise you might connect to every partition sequentially. You don't want to do that. That's important to make sure you pick an appropriate one to make sure that you get the best performance. Okay. How to detect hard partitions. That's an important one. That's a critical one, actually, because that can kill your costs. Okay. So what does a hot partition mean? A hot partition means your partitioning strategy was wrong and you end up putting a lot of load into a single partition. How can you really figure that out? So look at those 4 graphs right now. On the top left, we are seeing the provision per partition, throughput, and consumed per partition. It looks like we're consuming more than we provision per partition, which is bad, right? This is maximum consumed RU per physical partition. This is the maximum. This is not the average, but it looks like one of our partitions is using more than we provisioned per partition. And then I'm looking to the right. It says average consumed RU second by collection. And I'm looking, consumed by collection is less than provisioned. Okay, so keep in mind that, a collection is actually being distributed across partitions. So I am good if you will look at from a collection perspective. So I got enough RUs for my collection, but I have more requests per partition in one of the partitions. So the top left tells me that one of my partitions is not able to keep up with the requests. And then on the top right, the graph is telling me, hey, you are good with your, RU usage for your container, which is the sum of all partitions. Then I'm going, bottom left and looking at, hey, how many requests do I have per minute? It's good. It looks like I have all HTTP 200s. Then I'm looking to the bottom right, number of requests exceeding capacity per minute. Oh, it looks like I have requests that are getting HTTP 429. So this picture shows me I got a hard partition. There's definitely a hot partition here. So if I go into the next slide, I go and simply look at my data distribution across partitions, and it clearly shows that the Seattle partition has a lot of data compared to all other partitions. And this is definitely, this might be one of the reasons that we're having a hot partition here, because it looks like, the Seattle partition, it looks like I decided to partition to use, the city name as a partition key. And if I end up having more customers in Seattle than other regions, then I am definitely going to get a hot partition. In order to be able to, keep up with this partition, I'm going to need to increase my container RUUs, right? Because the container RU is the one that I can set. I can set RU per partition. I'm going to increase my container RU to be able to keep up with Seattle, but then I'm going to have the same RU amount provisioned for all other partitions as well, but no one is going to be use those. So yeah, that's going to be bad. I will be paying for resources that I'm not using on all other partitions just to be able to keep up with the Seattle partition. Okay, so Cosmos DB serverless, this is coming soon. I just wanted to mention this. This is recently announced. This is consumption model. If you already use the serverless, stuff, Azure Functions, there's a consumption plan there. Azure API Management has a consumption plan as well. So you simply consume request units, you consume storage, and you pay only for what you consumed. And it lowers the entry barrier, right? The entry price for Cosmos DB. This is a great option for small to medium workloads that really, doesn't require huge amounts of throughput and, have this random spikes and so on and so forth. And this is really a good entry point if you want to use Cosmos DB and you really don't want to be, you're not able to hit even the lower limit of provisioning, limitations. We got auto-scaling. I did mention a little bit about this. What auto-scaling does is that you define an upper limit, and then as you can see on the right hand side on the screenshot, you pick auto-scale on the Azure portal and you define high, the top limit for your throughput, and you're based on the load, your resources will scale up, and if you don't use, your resources will go down. Yeah, I'm looking at the slide deck right now to make sure I'm not missing. Yeah, there's an increase in 10x range. Okay, cool. Custom max are unable to scale on existing workloads. Yeah, you can change the setting of auto scaling as well. The higher limit, the upper limit of the auto scaling, you can definitely change that through the APIs as well. So this kind of helps, you can scale up maybe, but you don't want to scale down, or you don't want to do it all the time, or where you're flying, so you can, set a maximum that is definitely it gives you a feeling of, hey, things are going all, crazy. There's no way we would hit that. There's definitely something wrong. Maybe that's your maximum, and you can live the rest to the auto scaling. We did talk about consistency levels, but I knew I had some more slides about those because those previous slides, somehow they didn't look well. Remember, they were duplicate, so I guess that's where we're good getting into those. So bundle staleness, we did discuss about this, so I'm going to skip this, but just to reiterate, number of versions or time interval is what bonded version was. We didn't talk about consistent prefix, and I knew I had a slide about this, and here we go, consistent prefix. So consistent prefix guarantees, and I'm going to read the slide, consistent prefix guarantees that reads never see out of order writes. Okay, never see out of order writes, but it can be stale. So the order of writes are always gonna be right, but you can get old data. So this is, keep in mind that this is somewhere between session consistency and eventual consistency. Okay, I'm just giving a pause because I know it takes some thinking if this is the first time you're hearing about this. Good. Multimodal, we did talk about this. There's a couple of, these languages and how they're supported in different APIs. I wanted to put this here in the slide deck because at the end of the session, I will give you this slide. So I'm trying to put as much information as possible so that you can grab those. Yeah, we did talk about this as well. Yeah. That's all. This is the resource model. I'm not going to talk about this a lot. I did touch on this in a previous slide, I did mention that, there's some kind of a projection based on the API that you are using, the underlying infrastructure in Cosmos DB. It gets projected to you with different words and names. For example, an item is a document. If you're selecting, SQL API, an item is an edge if you're selecting the Graph API. And on the top of this slide, you're seeing the primary, the original, resource model. So there are containers, items, attachment to items, store procedures, triggers, UDFs, and conflict management policies, essentially. And that is what it is. Depending on the API that you choose, you end up having a different projection so that you can use it. So we did not talk about indexing a lot. So we got a couple of different indexing modes: consistent indexing, lazy indexing, and none. So you can still do scanning, but it's going to be really costly. So you can define an indexing policy in the scale and settings tab if you want to. So the indexing policy helps you out to define how to index those types. If you want to have some specifics, or if you want to have some, I'm not sure how to say that, lower precision indexing, if that makes sense, so that you don't use as much compute and storage as possible. And then you can have different index types, or you can disable indexing per field if you want to. And this is, indexing policy is where we do these things. Okay. Yes, you should definitely, customize your indexing policy, based on your query, and you can, do that when you're creating the collection. You can even do that when you are, creating the collection with a code. You can definitely do those things. And there was a sample code that showed how to do that. What else do we have? Analyzing query performance. Yes, we did talk about this, but if you want to really have all of the metrics, we did talk about the cost of queries, but if you want to have all of the metrics about a particular query, the parameter that you can enable is, you can say populate query metrics true, and then you're gonna, get out a lot of various metrics that you can, use during your development or debugging, or, I don't know, maybe in your dev environment, or maybe even staging environment, or whatever, to take a look into your queries and improve performance. We did talk about SLAs, but we didn't discuss exactly what the 4 different axis SLAs were. So we got high availability SLA, that's separate. We got another one across regions. We got an SLA for throughput, latency, and consistency. We got an SLA for consistency as well. So all are at 99 percentile. So it's not just availability SLA. We got throughput SLA, which means performance SLA, right? Consistency SLA and latency SLA. When it comes to security, I want to mention a couple of things here. I'm not going to read the slide, but these are all the things that you can do. The 2 things that are kind of new is you can do, obviously, encryption at rest, that was available in the past as well. But what's new here in this round is customer managed keys. You can use customer managed keys to do encryption at rest. And then we got private link support for Azure Cosmos DB as well. There we go. Yeah, I always put this disclaimer in every Cosmos DB session that I do. Cosmos DB is not a SQL database, so don't think about it like a SQL database, because that when you start writing SQL code against something, obviously it makes you feel like you're against the SQL server, but we're not. So don't think about you're not gonna have complex joiners and stuff like that. It's not going to work. So keep in mind that you are always working against a NoSQL database, and keep in mind that this is a hosted, PaaS solution, and look at the full product and think about that perspective, because if there might be other databases, and there are, to be honest. I'm sure you can find a better document type NoSQL database product out there that is better than Cosmos DB. But what you have to look into this is, the flexibility, the 4-axis SLA, the geo distribution support that comes out of the box, where we don't even need to do anything about it. It just works. The read-write, multi-masters thing. Think about all these things and all the, being able to enjoy all these benefits from a simply, platform as a service offering, and being able to scale, scale up and down, and pay for, even, being able to optimize your queries to lower your costs. Think about all these benefits when you are comparing it with other products, because, if you compare it simply from a, query capability perspective, maybe, because, the thing is, when you start with a MongoDB API or SQL API, and you expect, every SQL command that you knew work on, SQL API, it's not going to happen. I mean, first off, just because it's not SQL, but second, still all of the, aggregates might not work, for example, just a clue. Keep in mind that, there can be better products out there, but they might not be native to cloud. So I have a couple of words worth sharing, links worth sharing. So Azure Cosmos DB has a beautiful YouTube channel. I strongly suggest you to subscribe to that. They have beautiful stuff going on there. And then we have, Azure Cosmos DB workshop with all the materials. I'm not sure what the third item is, so I deleted that. So the Azure Cosmos DB workshop, it's something, it's a website where you can have all of the labs and all this stuff, and download all of the workshop materials and run through the workshop on your own pace. That's a beautiful place to learn about Cosmos DB. And those are the two things I wanted to put up there. So thank you very much for being with me here. That kind of brings us to the end of this session. So I am gonna be still available on the chat Q&A box to answer your questions. Make sure you connect with me on the Virtual Networking Lounge as well. And by the way, you can see the slide deck link on the slide right now. This is where you can download the slide deck and grab all of the information in it if you want to. And thanks to Microsoft for supporting this conference, and thanks to all the community initiatives that supported this conference and made things happen. This has been so far a great experience, and I'm sure you're going to enjoy the rest of the conference as well. Yeah, it looks like, you can even post your selfies with the hashtag DPS2020. Make sure you fill out the, feedback stuff, give feedback to the, give session and conference feedback, because that really helps improving. You can follow the Data Geeks on Twitter, Data AI Summit on Twitter, and I had my own Twitter allies as well up on that slide deck, but in case you missed that, it's my name and last name. Hit me up on Twitter as well if you have any questions about Cosmos DB. And that's all for now. Again, make sure you send your questions. I will still be in the Q&A and chat area. Thanks for listening so far. Enjoy the rest of the conference.